Perfect. Yeah, so I'd like to get this session started with a round of introductions. If you can talk about your background, what brought you to crypto and zero knowledge proofs, and an introduction to your respective companies. We'll start with Tom.
Hi, I'm Tom Walton Pocock. I'm the co-founder, one of the two co-founders of Aztec protocol. So we're a layer 2 solution for Ethereum right now. We have kind of aspirations to go to other layer 1 protocols as well, but for the moment we're on Ethereum. We're privacy focused, so I think that's probably our USP. And as a company, we're known as the creators of Plonk, which is one of the major standards in snark-based technology, and I guess we'll talk about the differences between snarks and starks and other proof systems later. And in terms of background, I studied undergrad and postgrad maths at Cambridge in the UK, and then I was briefly tried to be a classical singer, tried to be a tenor. Didn't last very long, and then I found myself in finance for a few years in the shadow banking industry. Originally, Zach and I set up the company for a completely different purpose. We were looking to bring private capital markets to Ethereum for kind of the various obvious reasons you'd want to do that. Privacy was a problem, and that's what then led us down the scaling and privacy path.
Thank you, Tom. That's quite the progression, a career progression. Avihu, if you can.
Yeah, hi, everyone. So I'm Avihu, I'm head of product and blockchain research at Starkware. Actually, I started my background is in electrical engineering and physics, but during most of my professional life, I was a cybersecurity researcher. I was working around 10 years in all the different industries. My blockchain journey started around 2011. I remember I got an email from a friend saying, "Hey, look, this thing Bitcoin is very interesting. You should take a look." I was like, "Yeah, sure." And about a month later, he was pinging me again. So I did look, and that's where, that's where the journey started. It was my hobby for about 6 years, and somewhere around 2017, I heard about Eli talking about zero knowledge proofs. I found it to be like a great opportunity for me to join the space. So basically, I moved from cybersecurity to.
So sorry about that. I think
No problem.
Stream bombing. That means we've made this is like that means this is a real event now.
So that's how I joined Starkware. Basically, I've been in Starkware. We are focused almost from the beginning in building a scalability solution. Right now, we are focused on Ethereum. We are working with a technology named Starks. That's what Tom mentioned as well. It's after research by Eli and Michael, two of the co-founders of the company. I'm excited to tell you more about it in this coming panel.
Thank you, Avihu. Alex.
Hey everyone, I'm Alex. Some of you know me or have seen me before. I am a Stanford grad, GSB 19, and I used to be the president of the Stanford Blockchain Club. So it's a real pleasure for me to be back and to present to you all. I'm currently the chief strategy officer of Aleo, and Aleo is a platform for building private applications. So we're a new layer 1 blockchain that's implementing a protocol called ZKPs, short for zero knowledge execution. And it's, the way to think of it is kind of like Zcash for those that are familiar with the cryptocurrency space, except extended to, instead of just asset transfers, arbitrary programs. So I'm sure we'll get into all of this a little bit later. Quick background for me, for those of you who haven't heard it, I have nowhere near as impressive of a technical background as these two gentlemen here. I started my career in the U.S. Army. I spent 10 years in the military, spent 3 deployments in the Middle East, and I actually got interested in the cryptocurrency space towards the end of my time working with folks who were Syrian refugees. And from that experience, really got interested in financial liberty. And that's sort of how I found my way into Bitcoin, and then was fortunate to attend Stanford. And I got into cryptography quite deeply. Just, because I was interested in cryptocurrency, I decided to take a course that I was in no way prepared for at the computer science school with Dan Bonnet. And that really, to me, was the moment where I really fell in love with the discipline of cryptography. So anything that I've learned about the space has been mostly self-taught or through the courses I took at Stanford. But yeah, I think it's a really cool and interesting space. I was very fortunate after graduating Stanford in 2019 to have gotten an opportunity to be on the A16Z crypto team. So I was a deal partner there for almost 2 years, and yeah, led a number of investments. And that's when I got to get very deep into the space, the blockchain space specifically. And I came to realize after about a year that to me, I think zero knowledge cryptography generally, I mean, both applied to the blockchain space, but just in general, is one of the most, if not the most, underrated technologies of today. And so for me, it's a great honor to not only be here and tell you about it, but to also share the stage with these two gentlemen, both of whose companies, are leading the way, or helping to lead the way in the breakthroughs for the space. So I think all of us, I'm excited for you to hear from all of us, you as students, to hear from all of us about the different approaches and to hear really about why this technology matters and what it can do. So thank you very much for your time and attention today, and for inviting me here.
Thank you, Al. Alex, thank you for founding the club and consistently helping the club progress. We owe a lot of panels to Alex. Would love for you to give a brief introduction to what zero knowledge proofs are, just so our audience can have a baseline understanding.
Yeah, sure. So I'm just going to present quickly. So, and Avihu and Tom, feel free and weigh in if you think, if you have a different take on any of this. But I just kind of threw some slides together here. Let's see. Hopefully, you guys can you guys see my screen here? Hopefully you guys can see. It should say, Aleo, what is zero knowledge? You got it? Okay.
Yes, we can see.
Perfect. All right, let me present here. But yeah, so Tom and Avihu, please feel free and chime in if with your own take, or if you have a kind of a different opinion of some of this. But this is just really, the purpose of this is not to give you guys a class on zero knowledge cryptography. There's entire courses, entire curriculums have been designed around, educating people in this field. The purpose of this is just to give everyone a quick context. So I'm going to dip into some semi-formal terminology here for just a brief moment, but more than anything, this is just to give people a sense about what is the technology and what it can do. And so I'll lean heavily on a couple of different examples. And then again, in 5 minutes, we'll be through this and then we can get to Q&A, but this is really just to set the context. Okay. So zero knowledge, for those this is a complete layman slide. So what is zero knowledge, or ZK? Some folks may have heard this term. So this is short for zero knowledge cryptography, which is a subfield of cryptography that's concerned with proving knowledge of some fact without revealing it. Okay, so here's a semi-formal definition. And again, this is not a formal definition before I disappoint anyone with a technical background. But a zero knowledge scheme it consists of a tuple of algorithms, which is a setup, prover, and a verifier. And it has the following properties. So completeness, which is that any result computed within the scheme that's valid can be proven. And then soundness is that no one can compute compute a proof for an invalid result. And zero knowledge, which is the verifier of the proof, learns nothing about its inputs. Okay, so informally, what does this mean? So we imagine two parties, which is a prover and a verifier. And we imagine that the prover or some person has a secret that they want to prove knowledge of to some other party, which is the verifier. And so there's some interaction, it could be a repeated interaction, or it could be no interaction at all. But basically, there's some communication between a prover and a verifier, after which point the verifier becomes convinced, okay, the prover does in fact know the secret, and the prover doesn't actually have to reveal it. Okay, so what does this mean? Okay, now I'm gonna zoom all the way up and speak very informally. So I'm just gonna give you a few examples that I like to use to kind of illustrate what this technology is. So I know bars have been closed for like over a year, so I don't know if anyone actually remembers what it's like to go to a bar. If there may not be folks in this audience who've ever been, but if you go to like a festival or an establishment that serves drinks, a lot of times you have someone who just checks your ID at the door and then gives you a wristband, and then you go in. If at that point, once you have the wristband, if you want to order a drink, you can just go up and say, hey, I'll give you a drink, and then whoever's taking your order doesn't have to check your ID again, right? So the person at the door checks your ID once, gives you this wristband, and this wristband is effectively a proof that you are over the age of 21 or 18 or whatever the legal drinking age is, right? So of course, so you have to show your ID at the door, and then you can get drinks whenever you want. So zero knowledge, like I like to think of zero knowledge proofs as like replace the doorman with this cryptographic protocol. And then this wristband is effectively a way to prove to anyone that you are over the age of 21 without ever having to show your ID, right? And why would you want to do this? Well, think about when you show your ID at the bar to the doorman, right? Not only do they see when you were born and learn your actual age, but they learn many other things about you. Like, for example, my driver's license has my address that they shouldn't necessarily have to see. And this is kind of a toy example, like who cares about, if the doorman sees like my address or knows my actual age. But I think for a lot of digital, a lot of our interactions online, we end up revealing a lot more information than we potentially would want to. And so something like this is a nice technique to be able to, again, prove knowledge of something or prove some fact without revealing what makes it true. Okay, another good example. This is another one that a lot of people use. It's like, this is even simpler. It's like, okay, for anyone who's familiar with Where's Waldo, I don't know if actually anyone reads these anymore, but this is a puzzle where you're supposed to find some character with a particular striped shirt and hat. And so how can I prove to you that I found Waldo without showing you where Waldo is, showing you what the answer to the puzzle is? And so people can, kind of think about, okay, what if I give you a piece of paper, right, with a cutout, the exact shape of the page with a cutout of Waldo in the exact location where he should be. And I give you this and you can lay it on the page and then see, in fact, that I know where Waldo is because I've put the cutout in the exact right spot, but you actually, shouldn't really learn where he is. So this is another kind of toy example that people use to describe what a zero knowledge proof is. And then another one that's a little bit more formal is there's a problem in math called graph coloring, right? And this is, for those who aren't familiar with what graph coloring means, like this is just about like, think about a map where like every country that borders each other doesn't share a color, right? And so, this is it's a mathematical problem. And so if I want to prove that I found a solution to say, hey, I've got a coloring for this map, where no country, that it borders each other shares the same color, then I can say, hey, I can prove that I found this coloring without actually revealing to you what the colors are, without showing you the map. Okay, so this is kind of a very, very rough overview of what zero knowledge cryptography is. And I hope, Tom or Avihu, if you guys, have any others to add or caveats to make, feel free. The last slide right here before we dive in is just like, there's a whole bunch of terminology in this space, right? And there's a whole bunch of different approaches and different constructions that, have different, like I say, different assumptions, different strengths, different weaknesses, and designed for different purposes. But I would say don't be intimidated. A lot of the time, I think at the core, again, the idea is being able to prove knowledge of some fact without revealing it to a verifier, right? So I think those are just the core ideas that you guys need to remember as we kind of go through this. With that, I'm just going to stop and hopefully we can get in to the session. And hope Tom and Avihu, please chime in if you thought any of that was incorrect or if you have anything to add.
Perfect. Thank you, Alex. That was a good reminder for me as well. As you mentioned in your last slides, people have heard terms like ZK snarks and starks and plonk, and Tom will cover plonks later on. If one of you can just give us a very quick introduction to what's the difference between snarks and stark, and how the zero knowledge proof industry is progressing forward in trying to like experiment with newer ideas.
Tom, I think you're the person for that.
Well, that's kind. I'll be as impartial as I humanly can. So, yeah. So I mean, actually, I would say that the first thing is the terminology and language in this industry is universally confusing and is becoming very smudged now for a reason I'll explain in a second. But typically, or we've certainly go back sort of a couple of years, and we were sort of classifying these ZK proofs. There are some outliers like bullet proofs and various others, but typically we were talking about either snarks or starks. And a snark is a proving system that uses a kind of mathematical shorthand known as a common reference string. And really, this is it's a little mathematical ladder that's very useful as a shorthand. So if I'm trying to, for example, prove in Zcash that, and I have to work very hard to say Zcash because I want to say Zcash, but Zcash, if I want to kind of prove that I've done a legitimate spend, I want the amount of information that I have to tell, let's say in this case, the blockchain, to prove that I've done a spend that it doesn't double spend money, but keeps all of that information out of the way so the blockchain can never see it. A snark enables you to keep the amount of information very, very succinct. It comes at the cost of this mathematical shorthand. And when you create the mathematical shorthand, you have to do it through a computational ceremony that involves typically, I mean, in the very first instance, we're talking about 6 or 7 participants, and nowadays these ceremonies involve more and more and more people. And the trouble about these ceremonies is that they do have a weakness at the bottom of them. And so this is me being impartial, because we rely on a trusted setup at Aztec. And that weakness is, if I do whatever the computational ceremony is, and I hand it on to Alex, and Alex, you hand it on to Jen, etc. Let's say the whole call, we hand this thing round, then at least one of us has to forget the piece of information embedded into this computation. And if we don't make sure, if at least one of us does not destroy this piece of information, then you can fake proofs. Now, the difference between that and the Stark is, in the setting of a Stark, you can't fake proofs. So it does not rely on this mathematical shorthand, this mathematical ladder that needs to be created by a group of people. So if you trust the cryptography and the soundness of the cryptography with the Stark, and the letter T in Stark means transparent, there is no non-transparent part of the cryptography. You always know that's secure, whereas with a ZK Snark, you have to rely on the fact that at least one actor in this large ring of actors behaved well. But the payoff then comes that the amount of information you have to transmit is very small for a Snark and is much larger for a Stark. On the flip side, by the way, Starks, let's suppose we're talking about payment systems. Let's say we're doing Web3's answer to PayPal, and you're having to create this zero knowledge proof, which is going to be basically spending some money. I've got $10, I want to send you $7, I want to keep $3 out of the balance, and I want this zero knowledge proof to say, look at me, I didn't spend any money. Then the computation running on your computer could take quite a long time with a Snark. And at Aztec, all of our work is about pushing that time back down, making it really fast and run like PayPal. On the flip side, with a Stark, it runs incredibly quickly. So I hope that was a relatively impartial summary of the differences between a Snark and a Stark.
Yeah, and that's only the beginning, right? Like, so Snark and a Stark is sort of one way to define it. And then there's other proof systems that, Tom referenced Zcash, right? And Zcash is, okay, you're concerned with really proving one specific statement, right? Which is to say that, like, balances were conserved globally, and no one double spent money, right? But there's other systems, including Plonk, which Aztec pioneered, that Tom referenced, which is about proving arbitrary statements, right? So it's like not just this single statement, right? And so there's other schemes that do that. Then there's yet more schemes that kind of are concerned with how do you recursively tie everything together such that you can compress multiple statements into one, and on and on and on. And all of these come with different assumptions and different trade-offs, some of which that the same as Tom mentioned or kind of presented, the difference between Starks and Snarks. It's the same across all of these systems. And that's one of the really exciting, I guess the takeaway is, like, this is one of the really exciting reasons for me that it is to work in this industry right now, because it's a Cambrian explosion of approaches. I mean, zero knowledge proofs have been around since the 80s. And just to give you a sense of the pace of progress since, Zcash, the paper came out in the early 2010s. And, the first Zcash transaction in 2016, it took about a minute, as I recall, to submit a transaction on a commodity laptop. That time today is down to a second, right? Not only that, all of these different proof systems enable you to, produce proofs for all these other types of computations. And so again, this is just in the span of 5 years, this space has become practical in a way that it has never been before.
And actually the kind of the remarkable history here, I mean, the reason it all started, by the way, was nothing to do with the practical things we can use these things for today. It was in the 80s, people getting very upset about these mathematical proofs that were sort of blowing. I mean, you look at, for example, the proof of Fermat's last theorem, it's about 150 odd pages, creates new entire sort of kingdoms of mathematics in order to prove an incredibly simple statement. And so these theoreticians in the mid 80s, I think they were MIT based, I think I'm right saying it was Goldwasser, Macaulay, and I'm going to forget the last name. And they just wanted to prove, they wanted to convince themselves, is it possible, instead of handing over a sort of 150-page document proving some little theorem I want to prove, and having to do the round robin of saying all these statements that seem not always to be particularly relevant, but are kind of required in some circuitous way, and can I just actually tell you the thing is true and prove it and say, don't worry about the details. In other words, I don't want to tell you all of this extraneous information. And of course, that then had consequences for privacy, because if you can prove something without providing the extraneous information, then you can create these private setting proofs. And by the way, this S succinctness, which means I'm not going to send you a lot of information when I prove these things to you, also has implications for scaling as well. And Alex was alluding to, he said, recursion. You can use these things not just to keep things private, but also to save the blockchain from having to check lots and lots of things and give a tiny little nugget of mathematical proof.
I wanted to mention just this small difference is also important. I think most people first instinct when they talk about zero knowledge proofs, they think about privacy. Zero knowledge is part of the definition. But as a matter of fact, like you can, and we actually do, target another property of zero knowledge proofs, which is the ability to verify proof in a time which is like exponentially smaller than the time that it takes to run the computation. And in fact, for our use case, which is scalability first, zero knowledge is not even necessary and would even slow the prover with some small factor. So we can actually generate proofs that are not strictly zero knowledge, but still provide a scale.
Yeah, and let's just to linger on that, because I think this is a really groundbreaking and beautiful result in computer science, right? This notion that an NP statement you can verify in polynomial time, this is like some jargon that some people may not be familiar with, but like things that are very, very hard to compute can be verified very, very easily in the scheme, right? And so you compress, as we were talking, Tom and I were discussing recursion and the way to compress lots of computation into a small space. This technique also allows you to compress time in a sense and verify some computation was done correctly in a very short time.
It's funny, Tom, that you mentioned about the mathematical proofs. I remember my mom, she's a math professor, and I remember her talking about something similar. And as a teenager, I did not care, but should have paid more attention to her there. But as we are on the topic of snark starks, bulletproofs, and all of that, you can now go into a mode of being partial to Planck's. And if you want to capture what Planck's does, that'd be great. And then we can touch up on scalability, which Avihu, I think you'll have a lot to say there.
Sure. Yeah. So I mean, what we do, I think which of these proving systems you pick depends very much on what is the thing you're most focused on and what are your constraints. Now, for us, our biggest constraint absolutely is Ethereum, where in a visible setting you can get about 15 transactions a second through Ethereum. And then if you make the transaction private, well, you can get about 1 transaction a second through Ethereum, and it just gets worse and worse. So what we care about is we need to keep, we can using, and I'll explain a bit what Planck does in a second, but we use Planck to make it very quick for Ethereum to verify all these private transactions. But where we really care about being a snark rather than a stark is we need to keep the amount of information that proves all of those little private transactions to the biggest snark. So you imagine I've got private transaction, private transaction, private transaction all the way along here. And what I'm going to do is I'm going to create what we call a roll-up proof, which says, don't worry, all these are true. Don't worry about checking it. I can save you that time, as Alex was saying. And you send that to me, but I also need to store these things somewhere. And so I don't want the information to blow up too much. So that's why we want in our setting to be a snark rather than a start, because Ethereum really makes you pay a lot of money to store all this information. So you want it as succinct as possible. Where Plonk was a big breakthrough is, I mean, as Alex said, with the Zcash system, it was what we call a single circuit snark. What that means is the trusted setup that I alluded to earlier, the DNA of the thing that you want to do in Zcash is baked into the structure of that trusted setup. And if you wanted to go and do something other than just sending some Zcash money, you could do it with that zero-knowledge proving system, but you'd have to do a completely fresh setup for that new thing. So you imagine you've now got a smart contract. You want to do some zero-knowledge proof over this smart contract and check that, you know, like a MakerDAO, or I don't know what it might be, but some smart contract that's doing something that's more than just sending money. Even if you just want to change a tiny piece of that code, you have to now do this 3-month trusted setup with nodes around the world doing these trusted processes and storing information every time the smart contract engineer changes a line of code. So that's clearly intolerable. What Plonk does is it has what we call a universal setup. It's a universal proving system. So you do it once, but the shape of that mathematical ladder that's been created is so universal. And if anyone's really keen on their maths, we can dig into exactly what that looks like. But it's a completely universal, what we call monomial scheme. And what this means is that you can prove any circuit that you like with one proviso, that the circuit can't get so complicated that it's bigger than the ladder, right? So there is a kind of upper bound to the complexity. But this is what Plonk brought. It was the first really efficient universal snark. It came also at the same time as another one called Marlin, and that was really the big breakthrough, is you could prove anything, not just one thing.
Thanks, Tom. And while we're talking about rollups and such, Avihu and Tom, both of you are working on scalability on Ethereum. Could you talk a little bit more about ZK rollups and what zero knowledge proof started off as privacy has, like, now in the ecosystem has really exploded into a scalability solution? So yeah, if you can touch on that.
Yeah. So yeah, I remember when we started, it was the only paradigm. Like if you do zero knowledge, you do it for privacy reasons first. And we actually started about the same time where there was the famous CryptoKitty mania or network congestion. And we spoke with a bunch of Ethereum projects, and we realized that with our technology, we are capable of taking a large number of transactions, much larger than the number that Ethereum can process, with the same cost, and generate a single proof that can attest to the validity of all of those. It was very early on. It took us time to get to a scheme that is looking more like the rollup of today. But we did start to work on it very early. And actually, so maybe I'll say in a couple of words what ZK rollup is. So right now in Ethereum, the way that Ethereum works is that everyone sends transactions to the network, and the entire network verifies them. And the goal in ZK rollup is to say, well, if I split, if I'm looking on transaction in the network, every transaction that everyone replay, you have to check some storage, you have to verify some computation, and you have to see some data. And the idea in rollups is to say, well, specifically ZK rollups is to say, well, if I will be able to generate you a proof that attests that I actually computed everything right, and that I touched the entire storage everywhere in the right way, and that I change it accordingly with this, in accordance with this computation, then you won't have to repeat the computation and the storage changes. You could just verify the proof instead. And so the only thing that the network will have to see is the data. And even from the data, only this subset that enables everyone else to know what the state looks like before and after this batch of transactions. So the way rollup work is that the network is familiar with the network knows a commitment to a specific state of the system. And with every state transition is basically taking this commitment, let's call it A, to a new commitment B, using proof verification that attests to something like, I've seen yay many transactions and I've checked their signatures, I've checked that they execute computation correctly, and I've checked that they change storage correctly, together with publishing the changes of this state on chain. So instead of paying computation, storage, and data, you only pay a subset of the data. And that's how you get scale or higher throughput. I just want to share, like, just so you understand the numbers. So today when we started with a product that we run until today that we call StarkX. It's a rollup for a single application. We hit mainnet with a spot exchange that is called Diversify. And we are now hitting mainnet with a derivative exchange that is called DYDX. And the number of transactions that we can produce, even on production. So in production with Diversify with a spot exchange, we approve up to 8,000 trades in a single proof. Where if you try to do the same on Ethereum, you would pay about 50 to 100 times more on the same number of transactions. So that's where we stand today in production on Ethereum.
Thank you, Avihu. Yeah, StarkX, I think it really goes after the DeFi pooling problem that we have today, and in order to like reduce gas fees and make it much faster. For those interested in learning more, I would really recommend reading the blog post on Starkware. They give a wonderful explanation of how they are helping Diversify and DYDX. Talking about privacy a little bit, Alex, if you could talk about how Aleo is integrating with Web 2 or Web 3 applications in terms of providing privacy, and what the developer's journey looks like, because you guys have an IDE that you're working on, and there's a lot of research that you've put into supporting developers create these applications. So if you can talk a little bit more about that.
Sure, yeah, and let me start by just piggybacking on what Avihu said. I think, because I think it's relevant for Aleo as well. Yeah, so blockchains, right, like, okay, so going back to Bitcoin, right, Bitcoin kind of invented this idea of crypto economic security, right? Before Bitcoin, there were all these schemes that people had for, cryptographic security for payment mechanisms, right? Hashcash and DigiCash and eGold, et cetera. And all of them relied only on cryptography, but it was Bitcoin that really pioneered this idea of like, hey, if we have miners, we can have like this crypto economic security guarantee, right? And then Ethereum came along, took that, married it to a virtual machine and said, okay, hey, now not only do all the nodes on this network need to like, come to consensus about the state of this ledger, but everyone also needs to basically run computations, and then collectively we're like a global computer. That's a breakthrough for obvious reasons, right? It enabled MakerDAO and Uniswap and everything, et cetera, et cetera. But as Avihu just pointed out, right, and Tom as well, like, when you have every computer on the network or every node on the network processing all these transactions, the throughput slows to a crawl, right? And so the key idea here that Tom and Avihu are both describing, that we at Aleo kind of, underpin what we're building as well, is this idea of separating execution from consensus in the state, right? And so you can basically zero knowledge proofs enable you to do this. And by the way, there's another approach to doing this. Like some of you may have heard of optimistic rollup, or TrueBit, or Plasma, and these are all relying on the similar crypto economic ideas or incentives that Bitcoin kind of relies upon to keep everyone honest. The cool thing about ZK rollups and ZK cryptography in general is that you enable these, you enable the execution to be guaranteed by cryptography, right? And so it's a much stronger guarantee of execution. Okay, now, so what is Aleo? Okay, so we've heard like, Aztec and Starkware, kind of, we've been talking in the context of Ethereum. So we've built Aleo as an implementation of some research called ZEXE, which is zero knowledge execution, which rather than building on top of Ethereum specifically, it sort of starts from the beginning and says, okay, like given this tool that we have, zero knowledge cryptography, and what it can enable, which is like, as I just described, the off-chain computation with on-chain proofs, like how can we build a system from the ground up, right? And so the way to describe Aleo in a technical sense is sort of like an onion of zero knowledge proofs, right? So, and this is how you achieve privacy at different levels, right? So as a user, right, initially I want to run a program, I run the program, create a proof that ran correctly. And then I create another proof that wraps around that proof that says basically, hey, that proof was correct. And then a third proof that to say, hey, that proof was correct. Now, why in God's name would I just create all these proofs? Well, the reason is that each layer of the onion, you're hiding a different thing, right, about the computation. So in the first layer, you're hiding what were the inputs to that computation. In the second layer, you're hiding what was the function that was interacted with, right? And so this enables you to get privacy all the way through. But critically, there's another aspect of this technology we haven't touched on yet, which is this idea of a view key, right? And Zcash, this is a feature of Zcash, which is it says, hey, I did this private transaction, Jen and I, are transacting. But if the FBI knocks on my door and says, hey, prove to me, like show me your transaction history and show me that you weren't, funding some terrorist organization, I have the ability to reveal selectively information about the transaction, which is critically, and I want to make this distinction clear, this is not an option that you have with every cryptocurrency protocol that is private. For example, Monero, right? Or some others, it's very, very difficult, if not impossible, to actually reveal what happened. And that's because it has stronger privacy, or they view it as a stronger privacy guarantee for everyone on the network if no one can reveal their transactions, right? So so anyway, so the purpose of this kind of multi-layered onion for Aleo is to create basically privacy all the way through, but of course can be tuned according to the user's preference or the application that you're interacting with. And to the point that you just raised, Jen, one thing I want to highlight, which actually Avihu can probably talk about as well, is from a developer experience standpoint, like we've been talking about zero knowledge proofs at kind of a high level right now. But like from a developer experience standpoint, like what does it mean to write a program that runs in this environment, right? Or that creates a proof? Like it's actually not trivial at all, right? I mean, I think already blockchains are kind of difficult to reason with, but here you have this additional complexity based on the fact that like the program that you're writing or what you want to have happen has to compile down to something very, very different than a program that runs on your computer, right? Without getting into technical details, basically the plumbing underneath it all looks very, very different. And so for that reason, we at Aleo have kind of taken the approach of going to building like a full stack developer experience where we have our own domain specific language for writing relatively high level logic, and then a compiler that takes that logic, compiles it into effectively the language that you can generate a proof from. And so that way, from a developer standpoint, it's the same as writing kind of Rustish or JavaScript-like code, but you'll be able to create proofs about that, right? But again, another difference and distinction here is, what does it mean to have state? What does it mean to have a program in this scheme, right? Because it's slightly different. Again, when you're talking about privacy, and you want to prove something, that's different than just running a program with some input and getting some output, right? In this model, you're taking some inputs, running a program, and proving that some output happened, not showing the output. That's the whole point. So again, because of all this nuance, this is why that number one, this is a reason why it's been hard for developers to kind of enter the space. And number two, the reason that we decided to take the full stack approach from building the IDE to the language all the way down to the blockchain to make it, all kind of integrated and work together well. But like I said, Avihu, maybe you have some thoughts on that too, since I know you guys have a smart contract or a language for Starkware.
Yeah, maybe I'll say like the history that brought us to this. So we are working on Cairo for a very long time now. I don't know exactly how much, if that's already 2 years. The point was that when we started with StarkX, the people who could actually write the logic to generate the proof there were very few people. It was very complex. If you want to do it efficient, you have to write by hand, so mathematical constraints for every function. So you can do it if that's a specific program, maybe it's I don't know, the best comparison that I have in mind is the difference between designing a circuit for an ASIC and between writing a program for a CPU. So at the beginning, we designed circuits for ASICs, and it was very, very hard. With every new program that we wanted, with every new version, with every new feature, not to mention new customer, we had to like take a very small number of people to generate these circuits. That's mathematical constraints. And we understood that we can't work like this for ourselves, definitely not the outside world. So we built Cairo. Cairo is a language that enables you, you can write in a language that looks like other languages. It's not, you don't feel the difference that much. Although there's some deeper concepts are important to understand. Writing the language is pretty simple. And then you compile it and you can generate proofs out of the output of this compilation. And it turns out that we are capable of doing it pretty efficient. So not as efficient as designing an ASIC, but not far from being that efficient. And the trade-off is that you can write way more complex programs. So let's say that we have Cairo being slightly less efficient than a circuit, but you can write a program that optimize things that you end up being more fast than you would be without Cairo. So we ended up writing the next version of StarkX in Cairo. For many other customers, it became so much faster, not a bottleneck. And the real purpose that we intend for Cairo, or the main purpose now, is what we call StarkNet, which is not a product, but rather a platform where everyone, it's a layer 2 ZK rollup, but not a single app rollup, but a universe where everyone can write his own contracts in Cairo or her own contracts in Cairo, deploy them on this ZK rollup, and run them in a decentralized network that generate proofs. And to be able to do that, you can't force people to write mathematical constraints. You have to work with a language that is friendly and has all the power of our other languages. And this is Cairo, and we keep developing it. And there are a lot of tooling around that we are working on. There are a lot of tutorial, and I guess, Alex, that you are familiar with that. And I think Tom has also what to say about that. We actually organize Cairo workshops. You can take a look in our website or Twitter account to learn more about Cairo and how you can get familiar with that.
Yeah, and for those of you at Stanford, and I just want to linger on this point, because this is, like I said, this is truly the cutting edge. And what Avihu said is true. When you have a compiler, as opposed to wiring everything by hand, and the analogy he used is perfect, right? Like what these look like under the hood is much more akin to like a circuit in the real world than it is to, like, how you would think of a, like assembly code or something in a computer, right? It's a different paradigm. And, compilers for these languages are only just starting to be developed. Cairo is a language with a compiler that Avihu just described. Ours is Leo that we're writing. But actually, I was going to mention to the folks at Stanford, right, there's actually a gentleman by the name of Alex Ozdemir who does work on compilers, not just for zero-knowledge languages, but for SMTs and for other related kind of circuit-based type languages, and looking at unifying those different universes. And by unifying some of the, you find unifying these different kind of areas, you find there are efficiencies and optimizations that you can gain that you would never be able to do if you were wiring them by hand. And again, this is another example of how this is really, it's like a Cambrian explosion or a Moore's law, if you will, in this space where every year you have like these exponential leaps. And again, the difference in just 5 years has been pretty astounding. So if you guys are interested in this specific area, I highly recommend you check out Alex Ozdemir, who just gave a talk. I can share the link. But yeah, that's just another thing I wanted to add.
Yeah, I love how we started with applications and went down to compilers. So I'm going to tug on that thread and go one step further down. The ecosystem has been talking more about hardware acceleration for zero-knowledge applications and compilers. Could you guys talk about how you see the necessity of hardware in here and how that implementation would come about?
Yeah, so I mean, I guess Alex and I might have kind of immediately some different priorities on this, maybe to Avihu just at this point, which is if you believe in not wanting to broadcast the as it's called, the inputs, or they call it the witness to the proof, and there's the secret information you don't want to kind of broadcast. Then kind of third-party specialist equipment like FPGAs are a little bit difficult for us, because as soon as you're sending this stuff out, you're kind of risking the user privacy. So personally, for us, everything that we do is designed to be run through WASM. It's designed to be run through the browser, and choice that, amongst the other things that make all this stuff so difficult, that's just another thing you have to contend with, because doing things through the browser in WASM is did I disappear briefly, by the way? I'm sorry if I did. It says my internet.
For 10 seconds.
10 seconds. Oh, really? Oh, wow. Sorry. That's probably not such a bad thing. I'll try and say it more succinctly, but yeah. So we care about making everything run faster in the browser, and therefore we're not so. If, however, let's suppose you were trying to build, as one of our competitors, Meta Labs, is trying to build a recursion system that does everything that Ethereum does that in kind of a zero-knowledge proof, and then it wants to roll up lots of those proofs and just send one of those to the blockchain. If you don't care, if you're not sort of trying to make that system private, then FPGAs make a great deal of sense, assuming that you can properly disseminate this machinery so that the user isn't reliant on one centralized provider, and therefore appeals all the advantages of a decentralized network in the first place. But I think that's the thing I want to say on that.
Yeah, and I'll just add a couple things. So I agree. So yeah, like Tom, we care about enabling the maximum amount of privacy for the users of Aleo. That said, I think the one difference is in Zexy, the model that we're building on is so you can choose as a user to give up some level of privacy to outsource your computation and proof, right? So this is a trade-off that you as a user can make if you want to have, if you want to basically interact with an application that requires, like a larger, like a more complicated application potentially, right? And so that said, right, like in most cases, we imagine most people will, want to create their own proofs. But hardware acceleration is still important, and I hope that these types of cryptographic operations in hardware that underlie a lot of this proof generation gets increasingly baked into not only specialty hardware but commodity hardware. And people often forget that, the internet, like the cryptography that we enjoy on the internet, like really only became practical when algorithms like AES, which is a symmetric encryption scheme that TLS relies on, got baked in at the silicon level, right? Like it was an order of magnitude improvement. And an order of magnitude, you're like, oh, it's one order of magnitude. But for a user, like that's the difference between like a few milliseconds and like seconds, right? And it's like, oh my God, this is painful to wait through, right? And so I think in the same way, as these approaches become more widespread and we take them not only in blockchain, but hopefully even beyond to areas like gaming, et cetera, there's more incentive to build this directly into the hardware. And so for us at Aleo, this is like one thing that I'm really excited about to share personally. So again, we're not building directly on Ethereum, and that comes with trade-offs, but one of the advantages is we have our own layer one, which means we can roll our own consensus. And the consensus we're working with, what we're using is this consensus algorithm called proof of succinct work, which is just Bitcoin SHA-256 wrapped inside of a zero-knowledge proof. What's the point of that? Well, now you have miners that need to compute proofs in a universal scheme, Marlin, to basically prove that they found a block, right? Just like in Bitcoin. But like in Bitcoin, we're hoping that this encourages innovation, not only like at the, for the algorithms and the underlying operations, but also actually innovation in hardware to make generating these Marlin proofs more efficient. And for us, at the core of our scheme, like for the users, the program proofs that users are creating, it's the same proof system. So hopefully the dream is that as miners get better and faster at producing blocks, some of that should translate to users and interacting with applications, right? Of course, not all of it will transfer, but the idea is to kind of bootstrap this idea. Because again, I think it is very important. At the limit, in 2050, I hope that these operations are baked in hardware and just commodity devices, not just specialty ones as well.
Yeah.
Sorry, did you have anything to add, Avi?
I just wanted to agree with I think that long term we will definitely see hardware that will fit for zero knowledge proofs generation. I think it will be more and more like as the use cases become more and more popular, we will see it more in the market. But now we devote most of our efforts into optimization on machines that are accessible either on the cloud or like a user accessible, even laptops. I'll just give an example. I think it was 2018, we received a grant from the Ethereum Foundation, and the grant was talking about yay many hashes per second to prove. And I think that levels were like 100 hashes per second, 1,000 hashes per second, and 10,000 hashes per second. And we were like, at this point, it wasn't clear that we could achieve 100 hashes per second on the same commodity hardware that was discussed there. By the time we reached the end of the grant, 2 years later, could already run 10,000 hashes per second. So there are all kinds of optimizations and work done by Aztec and Aleo and others and us to make these things already run faster, like way faster than it was possible 2 or 3 years ago. Some point we'll reach the limit, and then with use cases, we'll see also hardware get into the play.
Perfect. With that, I'm going to open up to audience Q&A. I think we already have a question from Shantanu Sharma. If you want to go ahead and unmute yourself and ask the question, please do.
Yeah, hi, thank you. This is very nice discussion. I learned several things. So my first I am from the database background, so not a cryptographer. So maybe my questions are not very relevant, or you may think. So the first question is regarding if I execute any encrypted query over the data, and I want to verify that the cloud is returning me the correct answer. So I took the example of, let's say I have outsourced 1 million rows using some encrypted functions like searchable encryption technique or MPC technique, and I want to execute the result verification. So can I use the technique of zero knowledge proof to verify the result? So this is my first question. And second question is regarding the scalability issue. So you said that you are dealing with some scalable thing in the context of GK proof, but how I can relate this secure scalability issue in the context of database? If I outsource 1 million rows, so what is the how should I interpret the meaning of scalability here?
Thomas, you want to give it a shot? I can give a first crack, and then you can weigh in. Okay, so great questions. Okay, so first, I think this is a great opportunity to also highlight that zero knowledge cryptography is just one of several like emerging areas in cryptography. In general, like I said, I encourage all of you guys to take a cryptography course while you're at Stanford, or just, there's an online Coursera version that Dan Bonnet released. I encourage all of you to check it out. There's several different related fields that are relevant to your question. So I think the first thing that I think of when you ask that is like, okay, does this sound like a better, something like homomorphic encryption a better tool for this job potentially? And for those of you who don't know what homomorphic encryption is, it's a slightly related technique to zero knowledge, though not the same, where fully homomorphic encryption basically would enable you to take encrypted data and compute some function on it, right?
Right, yes.
Yep, and then there's also, for the database use case specifically, there's a technique called oblivious transfer, which basically touches on this exact area as well, right? And so, so I guess the answer to your question is, could you use a zero knowledge proof to verify that the correct rows are being returned? I think the answer is yes. The question is, with that proof, what would you do with it? And would you be better served with one of these other cryptographic techniques potentially? I'd have to know more about the use case specifically.
Okay, yeah.
The things I'd add to that, first of all, homomorphic encryption is sort of prohibitively expensive at this point. There's been lots of advance on it, but it is still an extremely expensive thing to do. The second, of course, is you'd have to grant that whoever is serving the proof that they've returned you the right information from that database. This is where Alex's point comes in. Wouldn't homomorphic encryption, fully homomorphic encryption be better? In the zero knowledge setting, whoever's proving to you that they retrieved the right information would have to know what information they scooped up. So that's another thing. The other sort of final point I'd add is these circuit sizes. So you talk about 10 million rows. So we're already talking about a lot of little sort of bits of information. Maybe there are ways you can structure this that you can kind of reduce it down. But when the complexity of the thing that you're doing becomes very, very, very large, these proof times become very big as well. Now, actually, there are ways that you can kind of get around that. Like, for example, you could say, well, this zero-knowledge proof can go and work on this bit of the database, and this one can go and work on this database, and then I'm going to recurse them all and string them together and serve a proof. So there are ways that you can make that better, but a lot of these ZK proofs are kind of bound by how complex is the statement that I'm making. And if it gets very, very, very complex, then my proof times get really high, and I have to do something extra clever structurally to kind of push those times back down again.
Perfect. I want to be mindful of everyone's time, but Tom, if you have time later, would love to hear a little bit more about Aztec's 2.0 mainnet launch and ZK Money that Aztec has been working on. But before that, I want to tell everyone, Tom recently wrote a piece on Medium called What Mark Cuban Taught Us About Privacy on Ethereum. It's a very entertaining piece and explains the privacy issue on public blockchains like Ethereum and the implications of it. Please go and read it. It talks a lot about NFTs too for folks who are really excited about that right now. One additional thing I wanted to say is if you are interested in learning more about zero knowledge proofs, there's a podcast called Zero Knowledge Podcast that is hosted by Anna Rose and Frederick Harrison, and Alex Pruden helps them with that. So please go and listen to those podcasts and read those blogs. They really break it down to very simple, digestible tidbits. So please do that. I would say thank you everyone for coming, but Tom, if you have a couple of minutes, would love to hear from you about Aztec's mainnet launch 2.0.
That's kind, Jen. Yeah, so we're finally about to get our recursion service, our layer 2 service out on mainnet. It's going to be sort of slapped with health warnings at this point because we're releasing very, very novel cryptography, and it's going to take custody of people's funds. So what we're going to do is keep a $1,000 cap in place for a while yet. That also allows us to work out a few compliance issues, which obviously it won't surprise you to hear. We're definitely concerned about, and we're working through these sort of compliance issues at the moment. So first of all, it's going to absorb ETH, so you'll be able to kind of deposit ETH through ZK.money. You'll be able to send it completely privately and at a vastly reduced price to a public transfer on mainnet, and then withdraw it. Of course, I mean, what Alex mentioned earlier, the difference between a ZK rollup and an optimistic rollup. The benefit here is when you withdraw it, you get your money straight away, or at least as soon as the next rollup comes around. And the difference between this and an optimistic rollup is that you would traditionally have to wait kind of a week or two to get your money out of the system. We're then going to introduce further ERC20 tokens into the network, and then we have our language Noir, which is it's comparable to Leo and Cairo, a bit more like Leo maybe because it's Rust-like and has this kind of privacy focus, and that will be introduced into the rollup later this year. I think that's what I want to say.
Perfect. Thank you, Tom.
Recording in progress.
All right. Alex kindly said he'll stay for a few extra minutes if anyone else has questions. I would like to thank all of the panelists before that, and Avihu and Tom, if you have to jump off, please feel free to. It was such a pleasure having you, and love the spectrum from barely knowing anything to getting deeper into zero knowledge. This was wonderful for our students. Thank you.
Thank you very much. Yeah, it was lots of fun.
Yeah, thank you.
And on that, it looks like Adrian has a question.
I'm wondering about the security of these compilers, or maybe also the person that prepares these circuits, like it was in the past. So as a user, I would have to trust this circuit preparer, and I have to trust these compilers to an extent. Can you tell how they compare and how you make sure I can trust them?
Fantastic question. I'll go first and I'll let Avihu chime in. But yeah, like that is, I'm so happy you asked that, because that is, it is such a good question, right? And why is this a good question? Why is this important? Right. Well, we're writing programs in this kind of zero knowledge context, which means that, like, you know, once the program is compiled into a snark, right, you're creating proofs about this program, right? And if there's a bug, like either if the programmer introduces a bug, but more insidiously, if the compiler introduces a bug, there's not really a way to know. And in fact, some of you may remember this like kind of philosophical question came up with Zcash. It was a couple of years ago now, but someone discovered a bug that had been introduced, I think, in the programming process, where it would have allowed anyone to mint an infinite number of Zcash, or an arbitrary amount of Zcash. And the question was raised, well, like, did this bug get exploited? You know, because the researchers at the Zcash Foundation caught it, but, you know, people ask the question, well, did it get exploited? And the answer is no one knows. It actually could have been exploited, right? But the nature of Zcash is such that, right, shielded transactions hide the, you know, the payer, the payee, and the amount. And so there's really no way to know if there's, you know, if the Zcash amount, you know, is, you know, is like, you know, what, I can't remember the hard cap, 21 million or whatever, but there's no way to know if that bug was exploited. And so for us at Leo, with Leo rather, we're taking the approach of formally verifying the language and compiler. So we're working with the folks actually at the Kestrel Institute, which is based in Palo Alto, which is their specialty, to do that. And I think to us, this is a really critical piece of our roadmap, because again, compiler bugs in this case could potentially be critical to the functioning of programs. And so obviously formal verification is not a panacea, but to us, you know, is something that's very important for us to achieve before we release Leo in production.
Thank you.
I think Elliot has a question.
Yeah, this is a question for you, Alex. So I've seen a few different like smart contract platforms that are aiming to have like full privacy, you know, fully encrypted computation as well as inputs and outputs. And that kind of raises a question of like composability, because what makes Ethereum so vibrant and so incredible is that like you have all these contracts talking to each other, the APIs are open. And so like, how do you make like a platform that allows like private computation, but also talking to other smart contracts?
Great question. And I'm going to give you like, you know, kind of I'll take the opportunity to kind of give everybody a little heuristic that I like to use as an investor at A16Z when looking at these different approaches, right? And the question to ask with like any new product or pitch that you get, in my opinion, the two questions are, under what assumptions is this true? And what are the implicit trade-offs being made, right? And so your point, I think, is right on, Elliot. So if you imagine like something like Aleo, right, which is fully private all the way through, like I've got, you know, I'm hiding the amounts, the identity, the program I'm interacting with, like how do you create something like Uniswap, right? Which is sort of this contract, you know, and there's the state that's global on Ethereum that all this, you know, all the nodes, you know, they process state updates for. Like, how does that map to Aleo? And the short answer is you can do it. There are techniques, and there's some forthcoming research that I'm really excited to see published that'll be coming out in the next couple of weeks about NYU, about how you specifically make a Uniswap in the Aleo model. But it is different, like slightly structurally different than you would do it in Ethereum, right? And this is a consequence of the fact that in Aleo, we're trading off, in a sense, the advantages of transparency for privacy, right? And so as a result, state and data availability is a real big question, right? Because when you think about a program, like what does it mean to run an application or a program? Typically there's users, and then like users are interacting with some state, and then that state is getting updated, and then the new state is being rendered, right? That's sort of what a program is, or an application. I think of an application that way. But if everything's private, like what does that actually mean, right? You have to basically account for that state being off chain, and then how are you sharing the state? And then it gets to a whole mess of questions, right? So the short answer for how we think about composability on Aleo So there are some specific approaches that do maintain the privacy of a Uniswap type contract. But I do think there will inevitably be applications where users of those applications are okay with or implicitly give up some level of privacy to have this composability. I don't think there's any way, unless you get to a world of practical, formal, fully homomorphic encryption, for that to not be true. And so again, this is why for Aleo, like we have like this onion of proofs, and like in each layer you can use a view key to reveal the contents of of whatever the proof contains, right? And so with that, you can more or less emulate the model of like a Uniswap on Ethereum, where there's this global state that everyone has access to through the records on the Aleo's blockchain, and then people can update those records through Aleo transactions. And yes, you're giving up a little bit of privacy. It's not as bad as just doing it on Ethereum, mind you, where there is no privacy at all. But you are able to kind of replicate that same functionality. Does that answer your question?
I guess yes. It also kind of brings up other questions, which is like, how is state stored, and like, what does that execution environment look like? Yeah, so the execution environment, the execution happens entirely off chain with Aleo, and I think most of the I don't want to speak for Tom and Avihu, but I think that's sort of like the paradigm that we're discussing here, right? We're separating, like the key idea is to separate the state from the execution. And the advantage of ZK rollup on Ethereum, which is again like separate from what we're working on, although you could view Aleo, you could theoretically plug it in and it could work this way, but like the idea of rollups is that state gets blobbed on Ethereum, execution happens off chain, right? And so yeah, but I think it's important to note too, with as far as composability goes, with any layer 2 solution, right, you're only composable with the other contracts that are within that layer 2. Even something like optimistic rollup, right, which supports the EVM natively and Solidity contracts. If you have a contract that just lives on Ethereum but it hasn't been ported to Optimism, it's still not, you're not going to be composable with it, right? This is one of the reasons why I think the optimistic rollup solutions on Ethereum are not ideal. Because as Tom pointed out, there's a delay when you withdraw your funds or you withdraw your assets from a rollup chain and you move it to somewhere else, right? Which can be days long, which to me kills composability. I guess is much more of has dire consequences for composability, more so than something like ZK rollup, where, okay, even though you're maybe limited in the types of applications that are there, you can withdraw very quickly and transfer things around.
Yeah. If I may add one more thing on that, with ZK rollups and composability, you can even consider a program that executes something on layer 2, and then when the proof hits the chain and when the state transition happens, because it's immediate, you can do things on layer 2 that are dependent on execution of other things on layer 1. So you can actually have some form of composability between layer 2 and layer 1. And I think Jennifer mentioned earlier DeFi pooling. So both us and I think Aztec wrote about it. It's basically the idea that says where you can have your users in layer 2 communicating and signaling what they want to do on layer 1. And then all this communication and signaling happen on layer 2. But at the end of the day, you just do a couple of transactions on layer 1 based on their wishes. So that's another kind of interoperability between layer 2 and layer 1 that we can do with zero-knowledge proofs, but it's much harder to do with optimistic methods.
I will say the difficulty of what Abihu just mentioned actually is you do need, as a roll-up provider, you're essentially sending buses of collective transactions back to mainnet. And so, one thing I would concede on this point is that you need to be dealing with quite liquid, quite homogenized types of transactions in order to be able to get scaling for any layer 2 to kind of collectively act as a single economic unit. I need lots of the same transaction type in a single roll-up that goes back to mainnet. So that's the kind of caveat there. The other thing is I think in defense of optimism, there are credible reasons to believe that basically sort of very low fee financing could help to, rather than a computer science answer, you might find that low fee financing will actually be able to bridge the withdrawal delay. Now, obviously, if someone actually is, let's say, is sort of wanting to take some DAI off Optimism, right, which is a very stable, very reliable asset, supposing DAI exists on Optimism, and then they want to put it, they want to speculate it on mainnet, and that's going to be the collateral for that DAI going back onto mainnet, and they lose all their money because they put it into something very risky, then obviously that financing is going to blow up. So that's a kind of, but I think the financier's answer rather than the computer science answer is likely to be the way that Optimism solves that problem of composability between layer 2 and layer 1.
And by the way, these two solutions don't have to exist exclusively. Like, for example, let's take an example of like Aleo bridging to Ethereum potentially, right? So Aleo's got block times that are different than Ethereum. It's two different models. And so, and the Aleo side, like you can implement like a light client, it would be inside of a proof. And, you're basically just pulling state from the Ethereum chain and proving something about it. But on the Ethereum, like I said, because of this mismatched block time, there could be this issue where like, okay, something happens and it's like, kind of in this interstitial space as the blocks are moving at different rates, right? And so you could imagine like some of you are familiar with Keep, which is like a BTC to ETH bridge. Like you could imagine that having, there being like some optimistic kind of roll-up-y solution or crypto economic guarantee about funds for some certain amount of time before the cryptographic guarantee kicks in and says, hey, look, this is a proof that this asset transfer occurred, right? These two things can actually work together in a very powerful way. And again, I'm using this kind of bridge example here, but there's no reason that you can't imagine a hybrid layer 2 to work in kind of a similar way. I also quickly just want to return to Elliot because I didn't answer his question and make a point about this because it's important. So in Aleo, the records, so the state is entirely on chain. All the records are, and its state is in the form of records, which is similar to Zcash. And so that exists entirely on chain. What does that mean? The chain is bigger than it would be in some other instances. And I think I would like to compare it specifically to Mina, right? And some of you guys may be familiar with Mina in the privacy space, and this is the idea of a compressed blockchain. It's great, it's incredibly cool how they're able to take the entire state of the ledger for all time and compress it down into a single proof, right? The trade-off with that is, like imagine you lose your Mina wallet and you have to like restore from seed and you plug back into the Mina network and someone just sends you a single proof. Like what does that mean about your transaction history, right? Like how, you're like, okay, wait, what was my transaction? Like, how do I, this is like, again, this is like a really important point I want you guys to remember is data availability is a crucial, often underlying unmentioned assumption about all these scalability schemes, right? And where is the data being held? How is it being retrieved? And what are the guarantees around that? I think are very, very important to consider. So for Aleo, we're making the trade-off that data is always available. And this is the same trade-off that rollups are making, by the way, versus something like Plasma. The data is always available, and that comes at the cost of, in the case of rollups, right, you're not getting as much scalability as you could if you were running something like Plasma. And in Aleo's case, the chain is going to be bigger than if you were doing something like Mina.
Perfect.
I'm surprised we haven't heard any question about NFTs and scalability. So yeah, that's good.
Yeah. Perfect. Thank you so much, everyone, for coming. Also, for folks here on campus, we're really excited, and off campus, we're excited about Zero Knowledge. Please look to each of these companies and figure out a way to help them, bring their product forward, both on the research, technical, as well as business development and such. You all know that's how the ecosystem works. And yeah, so I encourage all of you to do that. All right, thanks everyone for coming.
Yeah, thank you everyone for coming. And I would just quickly say to plug, there's tons of great resources out there to learn more about this. I'm happy to share some with Jen after that she can share around. I'm speaking for us here at Aleo, but I'm sure this is true of Aztec and Starkware. There's tons of opportunities for getting involved in the space, from engineers to operations to business development. So please reach out if you guys are interested in any of those. And we've obviously got all those up on our website. And if you're just curious about, for me personally, again, since I was at Stanford and kind of made the transition to the blockchain and zero knowledge space, if anyone's just curious about, kind of my career trajectory and how I navigated that, I'm happy to talk about that as well offline. Jen has my contact info. Jen, feel free and share it with anybody who attended. And yeah, thank you guys very much.
Perfect. Thanks everyone. Thanks Tom, Avihu, and Alex.
Thank you.
Thanks, Jen.